Hi, and welcome to the second video in an Analysis 2 series. In the last video, the introductory one, we looked at the basic topology ideas such as open and closed sets, metric spaces. We looked at two different kinds of metrics on R to the n, which were the Euclidean and the supremum metric. We looked at the formulation of continuity in two different ways from the epsilon delta viewpoint and also its equivalence to the pre-image of open set definition. We looked at limit points of a set being defined for something in a metric space. We looked at closure, interior, exterior, boundary as operations that one can take on any given set in a metric space, or a space in general, rather. And now we're going to dedicate this entire video on the study of compactness and connectedness, both of which are essential topological properties of not just the real numbers, but R to the n, and of general spaces. So we're going to look at compactness first, which is kind of the, at first, the less natural of the two ideas, because it's formulation of a finite covering or a subcovering, and we'll define how it works in this manner. The Heine-Borel Theorem, a fundamental result in analysis, will be restated here. So we just take the idea of a metric space. So let x comma d, as usual, be a metric space. Now we define the open set, which I will rewrite here. Sorry about that. Which is going to be with respect to a central point. And I will write some scalar lambda, because to show that kind of epsilon has the connotation that you're taking something extremely small. That is, you're defining something with an arbitrarily small neighborhood, something that can shrink to however little you'd like. But lambda kind of keeps it general because we're going to define boundedness as well. And so we're just going to use this as to be some element in the real numbers. We have all x in big X such that you have your distance between x naught, which is going to be less than some lambda. Okay, so here's our formulation of the open set. And we will define two key notions for compactness now. A subset, sorry about that, A of x, or A in x, is bounded if you can find some lambda, so that if you take a neighborhood sufficiently large, you can contain all of A inside it. So to make that mathematically precise, if there exists a lambda in R such that A contained in the lambda neighborhood of x naught. So this is boundedness, bounded in a lambda neighborhood of x naught. And that's our first notion that we need. And our second one is going to be that of a cover. So we let A be in X, a collection, or just how I've been abbreviating it, U sub alpha, alpha with respect to some indexing set of sets in X, where, of course, now U alpha is going to be for all alpha in this indexing set I. Each of these sets is going to be in X. So this is going to be a cover of A. Our subset, colon should have gone here, no matter. If we have A contained in their union, right? So we have A, which is going to be inside this union across all of these U alphas, right? And basically what this is saying now is if you take a bunch of sets and you take their union so that you have now this large collection of set, you're considering all of the points that these sets cover, you can contain A in it. So they cover A in a sense, or they contain it, right? For any subset A in R to the n, we're going to define one formulation and then motivate the definition of the general case of compactness. I know that Rudin does this opposite, I think, gives the definition of compactness and then presents the Heine-Borel theorem. We'll do this in the opposite order. So our definition, A in R to the n is compact if A is actually, this is a stronger than if, and I should have been careful with that. If and only if A is closed and bounded. This is our working definition of compactness in R to the n, and just from the real numbers generalizes like this. So if and only if A is closed and bounded. Okay, so that is true for R to the n because of a property known as completeness, but it doesn't necessarily hold true for general metric spaces, right? You can have a set in some other metric space that is compact based on the general definition that is not necessarily closed and bounded. So you don't necessarily have this if and only if statement for everything. Here is the Heine-Borel theorem. Sorry about that. So let A in R to the n be compact, and we saw closed and bounded, so we let U sub alpha indexed by I be a cover, be an open cover specifically. So a cover consisting of open sets, as the name suggests. So this be a, Then finitely many of U alphas cover A. So what this is saying is that by this Heine-Borel theorem, which we'll prove in an instant, or sort of outline, we have a set that is compact, and we have for any open cover, we can take finitely many of those. We can choose finitely many, discard all the rest, and those finite collection of sets will still cover A, right? So every opening cover, let me formulate this properly. Every open cover of a compact set has a finite subcover. And in fact, what I've just said is the general definition of compactness, which leads to the Euclidean, so R to the n definition of compactness if and only if as an equivalence to closedness and boundedness. Here is our sketch of the proof. So let's do this first for some very simple compact subsets, right? Consider boxes, which is going to be products of closed intervals, where we have, let's say, B here, or yeah, B is fine. So B equals I1, let's say, Cartesian product through I sub n in R to the n, where I sub k, is going to be equal to some closed interval A sub k, B sub k for all k, right? So you just have a product of open closed intervals going to give you this rectangle-like thing, sort of box. So starting with our first dimension here, we have this set. It is closed and bounded, and it has the so-called Heine-Borel property, and that is going to be compact, right? So if we have this compact, then we have a product this times, we can use induction on the dimension here, so the number of products here. This is good to write out fully, and we can use induction to show that any product of these closed intervals is going to remain compact as long as their constituent kind of closed one of their sides is going to be compact in its corresponding singular dimension. So now consider, since we have kind of outlined compactness for these closed boxes, now consider a general compact here. So let's take A to be this compact subset. So A is closed and bounded, right? So we can take A bounded to mean, we remember that now open sets and closed sets are going to be whatever's open in the Euclidean metric is going to be open in the supremum metric, and so you have this kind of correspondence going on, so they define the same topology, and by stating that something is closed, you can state that there is a closed, you can say it with respect to the supremum metric just as easily, where if you have A bounded, then you can take a rectangle B, let's say, so a box B, abusive notation here, please take it with a grain of salt. So you have a box B such that A is going to be contained within B by this boundedness property. So bounded within the Euclidean metric implies bounded by the supremum metric, and that's what we're using here, and the converse because they define the same topology on R to the n. So now we we suppose is a more precise word here. Suppose we have this collection use of alpha for alpha, and I is an open cover of A. Then define or construct this U naught, not such that R to the n minus A. So you're taking the complement of A with respect to R to the n, so everything outside of that, and include U naught in this open cover here, right? And now we can include U naught in the open cover for the reason that we take A to be closed and bounded because it is compact, and since it is closed, we have this complement with respect to R to the n to be open. So if we have the set U naught to be open, we can include it in the open cover, just nothing restricting us from doing that. So we include U naught in this open cover. Okay, so we have B, which satisfies the so-called Heinne-Borel property, which means that they can be covered by finitely many open sets, right? Because we showed this by induction on these closed intervals that constitute their product. So we say that B has the Heine-Borel property, and hence, if B is contained in this cover, including U naught now, sorry about that, maybe I should just specify this. U is going to be contained in this whole thing as an open cover, because of course U naught is just the complement of A in R to the n. Hence, there is a finite subcover which contains B. By its compactness, or Heine-Borel, sorry, property. Right? Then we have this box B now, which contains A by construction, because we defined this this box B as containing A in the first place, which means that which must also cover A. by this containment, we have reached our conclusion because we found a finite subcover for our open cover of sets that, in fact, covers an arbitrary compact set in R to the n. So basically, let's just review what we've done. We've utilized the fact that the Heine-Borel property holds for these boxes in R to the n, these n-dimensional boxes. That is, they can be covered by finitely many open sets. Then we have formulated the fact that for any compact set that is closed and bounded, we use the boundedness property to define this box that is sufficiently large and containing it. And because of this, we defined a cover of sets for that box based on this construction of U0 over here, which we took an open cover of A, and then we took U0 to be an open set that is the complement of A in R to the n, where B is contained in this whole open cover. Since B is contained in this entire open cover, and we have it satisfying the so-called Heine-Borel property, we know that there is some finite subcover of this which contains A, because if it contains, which contains B, and then because of that it contains A. So this is what we've done here, and we've shown this, this generalized Heinenborough theorem for compact subsets. And what we have further is that what we've shown here, A's in Rn is compact if and only if it is closed and bounded. Now, this is one formulation, and we want to show now if A in R to the n has the Heine-Borel property, then it is compact. Okay, so let's look at why this is the case. And we want to show that the Heine-Borel property, which is that it can be covered by a finite subcover of whatever open cover has it. So we have an open cover of A, and that contains a finite subcover. And we take this finite subcover, and we take basically, we want to find the fact that it is bounded. So we have boundedness by finding a sufficiently large set that contains it. This is a good exercise to do and to fully sketch out just based on what I've said and how this might make sense. And closedness, we want to show that there's a slightly more difficult formulation, but I will leave that as exercise also. And I think I might create like a separate video just elaborating on this specific theorem, that if we have a set that satisfies the Heine-Borel property, then it is compact. But again, it's good just from maybe analysis 1 to recall this fact and work through it. So basically, now from this theorem, we're going to just derive the fact that if A has the Heine-Borel property, then it is in fact closed and bounded. Why is this? So we have compactness equivalent to closedness and boundedness. So we have something satisfies the Heine-Borel property if and only if it is closed and bounded. Okay. Now we want to show behavior of compact sets under continuous functions. You might recall from analysis that this is preserved under continuity. So we have our general notion now. Something is compact if it has the formulation that for any open cover you have a finite subcover. That's the general notion of compactness. And we take these two metric spaces, x equipped with d sub x and y equipped with d sub y. So I'll let these be metrics. Metric spaces f from x to y continuous. Claim: if A is, let's say A subset X is compact, so is its image set. F sub A, which is going to be in Y. Okay, so f of A is going to be a compact subset of Y, which means that compactness is a property that is preserved under continuous functions. Here's our proof of this fact. So let U sub alpha, again, alpha and I, be an open covering of f of A. The goal is to show that for an open cover, we can take finitely many sets and have a finitely generated subcover. So let this be an open cover. Sorry about that. F of A, which is in Y. All pre-images which is under F, so the F inverse of U sub alpha. For all of these, we had an open collection, so these are going to be open in X. Right? So now by the Heine-Borel theorem, which we're going to use in a second, we have that, first of all, the set of all of these inverses is an open cover of A, which is the subset. The subset in X. So Heine-Borel, finite subcover exists. And we'll denote this now, instead of this arbitrary alpha notation, we're going to index that alpha with just alpha sub I, which runs from 1 through n. Right? And it follows now that f of basically this whole set, basically, let me just write it like this, even though it's not technically how you're supposed to. It just means that f is carrying this whole set to its image, and what is this going to be for each f applied to f inverse of U sub A sub I? This is going to formulate this given set here. So you just take these indexed U sub alphas, so 1 less than or equal to I less than or equal to n, which covers f of alpha. Hence, we have found this finite subcover, which is indexed by these U sub alpha sub i's. I runs from 1 through n, so each of those sets constitutes a finite subcover for what we initially proposed as an open cover with just these general U sub alphas. For any indexing set, we have this to be compact. So f of A is compact because we found the finite subcover. And we're done with this. Okay. We have a corollary, basically, which is the kind of maximum point or extreme theorem. Let Ax be compact. Automatically, we know if we have fx2r continuous. Yeah, so as I was saying, automatically now we have the formulation of a continuous function, and by this previous theorem, we know that whatever f is, f applied to A is going to be compact. Compact in the image. So then f has a maximum, or let's say f attains a maximum on A, has a maximum point after proving this, you might want to ask yourself, why are we using compactness here? And why does this not necessarily hold for a non-compact set? So our proof, we have, sorry about that, we have f of a compact by our preceding theorem. Hence, we have the fact that it is closed and bounded. So now we have, by the property of the real numbers, the least upper bound property, which we will utilize here. Let this little a be the LUB, least upper bound, of the whole image set f of alpha, which of course maps to R. So it has this least upper bound by the formulation of a closed set. Now we have A to be in f of A because it is closed. And we postulate now, to finish this, there exists an x naught in A so that f of x naught just equals A, right? And we're done. This is our maximum value property. Here is another definition or property that we might use, which compactness allows us to formulate, and that is the idea of uniform continuity. So let f from x metric space to the real numbers be continuous. Once again, wherever we introduce a compact set in X, we know that the image is going to be compact, continuous. A is going to be a subset of X. So now, in fact, we don't use compactness immediately, but we put this definition here. Then we have a theorem which utilizes that. So we have F to be what is called uniformly continuous on A. If for all epsilon greater than 0, there exists a delta greater than 0, such that distance in X, so now that we just have one specified metric for X, we'll just leave it without a subscript, because this is implicitly for points in X. So distance between two points X and Y less than delta implies, I'll do this in the next line like I did prior. Now with respect to the absolute value of the difference of the images of these points, you have it to be less than epsilon. Right, sorry about that. Yeah, there we go. Okay, so this is uniform continuity for all pairs of points for all x, y, in A, right? So basically uniformly continuous if it is continuous across all of the points in a set. That is, you have this epsilon delta formulation where arbitrarily close points get mapped arbitrarily close points get mapped arbitrarily close under the image of a continuous function. Now here's our theorem, which I was alluding to, which utilizes the power of compactness. So if we have a function between two metric spaces, x to y, we have a continuous function in particular, and a compact subset of your domain, then f is uniformly continuous in A. So this is quite a strong statement. It's basically learned from continuity, when can you strengthen continuity to uniform continuity across a subset? So F is uniformly continuous across a subset, which is compact. Here's our proof. So let's take a step back and think about how we might go through this. So we want to, of course, leverage the previous proofs. So we take this definition of uniform continuity, and we want to tie it in some way to this compactness, which is now making its way in here, where we know the image set of A in Y is going to be f of A, which is itself compact. So how are we going to do this now? So we let, let's say P, little p be a point in A. Then there exists a delta P, so a delta radius with respect to this point P greater than 0, such that f of x minus f of p is going to be less than epsilon over 2, I'll explain this in a moment, for all x which is in this neighborhood. So about the point P of radius delta sub P corresponding to each point in A, right? Now this epsilon over 2 is allowed basically because we have this epsilon, and it's as if we had that definition, let's say epsilon naught or something, and we set that equal to epsilon over 2. Since they're infinitesimals, we can work with them this way. So we just formulate it like this. The absolute value of the difference of the images of x and p under f is going to be within, it's bounded by epsilon over 2 for all x, which is in this delta radius of a point P. So delta sub P pertaining to a point in your set. Then this collection of sets corresponding to each P, of course, is going to cover A. So we have defined a open cover, and now, of course, even if we just vacuously took this as small as possible, we still have open sets that just contain all of the points in A, so they must be an open cover. Hence, what we're going to do next is also allowed for the same reason that we took this infinitesimal epsilon over 2. So the collection of sets U about P, and now we're taking delta P over 2, we'll see why this is useful. P in your set A is an open cover, open by the neighborhoods, open cover of A. So now by Heine-Borel, finite subcover, and we will denote this finite subcover again as we did this notation above by indexing these alphas up here with the subscript I, which is going to run through the natural numbers. We'll do the same for these points P. So we'll denote them by U sub these points P sub I delta Pi over 2 for 1 less than or equal to the index I less than or equal to n. Then we choose now, out of all of these, let delta equal the minimum of delta, sorry about that, of all of these delta P sub i's, we take the minimum one. Sorry, this should not be bracketed this way. We'll just write minimum delta P sub I, divide this by 2, right? And we finish this with this claim, which shows continuity now. So, sorry. We literally just take this in this situation. Distance between x and y being bounded by delta implies f of x minus f of y absolute value is going to be less than epsilon, for however we've defined epsilon and delta. Here's our proof. given any x, select our p sub i's such that x is going to be contained in your neighborhood about p sub I with radius delta sub p sub I divided by 2. Hence, we have distance between each of these p sub i's, these indexed finitely many points. Right, we have this distance, which is going to be within delta p sub I over 2 by the formulation of distance with respect to a neighborhood of a point. And we have the fact that delta, by our choice, is going to be strictly less than delta sub p sub I over 2. Then we have this kind of chain of inequalities going on. So how do we solidify them, right? We have distance between p sub I and x is less than delta sub p sub I over 2, and we have delta is less than delta sub p sub I divided by 2. By triangle inequality, we can kind of string these together. Triangle inequality, we have distance now we examine between p sub I and y, right? So we have this by our construction or proposition. So distance between x and y is less than delta, which means that the distance between these points p sub I and y is less than delta sub p sub I. And it follows that if these two, if this satisfies this property, y is contained in the delta ball as is x, because we have x selected. We've been given an x and we selected this p sub I correspondingly. And now we have these both within the set p sub I, delta p sub I. Sorry about that. It follows now that we have both of these within this neighborhood, that the distance between f of x minus f of p sub I, right, is less than epsilon over 2 for 1, right? We have our continuity going on here for f. So we have less than epsilon over 2. F of y it should be. F of p sub I, which is less than epsilon over 2 itself. Now you see why this dividing by 2 came in handy, because distance is symmetric in this sense. Right? You're taking radii and reaching out from either end, and the furthest you can go to make that connection that meets in the middle is going to be epsilon over 2 if you have a distance or radial separation of epsilon between these 2 points. So you have this epsilon over 2 for each one. They're both bounded like this, and then you can add them. So you have the triangle inequality, you sum these two, and then you combine them like this. So now you have this distance less than epsilon over 2, this distance. Now you can take the distance between f of x and f of y, which is bounded by the sum of epsilon over 2 plus epsilon over 2. So this is going to be less than, which equals epsilon. And just for finality, I will write it in full here, is less than epsilon. And we have proved our statement. Okay, so somewhat of a long proof for this, but hopefully it makes sense. Just uniform continuity, compactness, and this is going to conclude our section on compactness in general. Now we'll briefly look at this notion of connectedness, and we will conclude our video. So we have a metric space x sub d is connected, or you know what? I'm going to define disconnected first. So I think separation is kind of more natural because you can define that, and then you can define connectedness as just something that is not separated. So a separation, this isn't exactly in the notes here, so please bear with me. I'm kind of just doing this based on my own recollection. Hopefully it's precise. So a separation of X is a pair, let's say U1, U2, of disjoint non-empty open sets in X such that U1 union U2 equals X, right? So a separation is if you can take your space and split it into these disjoint non-empty open sets, right? And those are your separated subsets, and if you take their union, they give you the whole space. If you take their intersection, it gives you nothing. So they don't overlap, but they still cover everything. This is your separation. And I will write in parentheses, just they have null intersection. Then we have the definition of connectedness, which we're more interested in. X is connected if it is inseparable that is, you can find no separation of X into disjoint empty, non-empty open subsets. No separation of X exists. So you can take all the open sets in X that you'd like, and you are never going to find two that are disjoint that give you the whole space X if you take their union. Here is a fundamental property of connected spaces, or the images, as we looked at images of compact spaces, and as we would very much like, the image of a connected space under a continuous map is itself connected. So let f be a function from, just writing this for completeness sake, because we're taking two different metrics, perhaps, d sub x, d sub y, between two metric spaces. Let's be continuous. So it follows, sorry, I think there's some calibration issue with my pen. Hopefully it doesn't persist into the next video. We're almost finished with this one. So X connected implies the image set f of X is also connected. Okay, what is our proof of this? So we're going to proceed by contradiction. Or not precisely contradiction, but let's say contrapositive actually is the more accurate term. Let's be precise with our proof method. So we're going to show if f of x is disconnected, then x is also disconnected. So you take, to show that something is true, you can show that its logical contrapositive is true. So those are both logically consistent with one another. If one is true, the other is, and if one is false, the other is. Important notion. So proceed by contrapositive. If f of x, the image set, can be separated, as this union, let's say f of x equals u1, u2, and they're both open, non-empty, then we want to show that there is a separation of x, which corresponds to our separation of the image. Right, then x is going to equal, this is a very natural way of doing it too. You take the union of separate inverses and by continuity of f, this is a union, a disjoint union of open sets. So it is going to be, since f inverse and f of u1 and u2 being inverse images of open sets in your image space y, then continuity of f implies that this is a disjoint union of open sets. X has a separation into f inverse u1, f inverse u2, right? So this is kind of a natural way of looking at it, right? So if you have separation of an image space, you can kind of trace your steps back to find a separation of your original space by taking the union of the inverse images of the separated sets. Because they're open under a continuous function, their inverse images are going to be open, hence those are going to cover your initial space X. And we're going to conclude this section and this video as a whole with the intermediate value theorem. You may have heard this in, I don't know, Calculus 1, probably more than just Calculus 1, definitely analysis. Let x d be connected, which I can just write as CTD sometimes. That's just my shorthand for connected. And we want a continuous function, x into r. Right, so notice these familiar cases, actually. We looked at for compactness, we took the special case that the codomain y is equal to r. And then we got out this extreme value theorem. And here now we're proving the intermediate value theorem by taking the image space equal to the real numbers. So these are really just special cases of more general theorems that we're proving topological spaces, metric spaces. And we're going to do this here. So if we want f from x to the real numbers to be continuous, if we have this linear continuum, and I'm not going to do that precisely, or define it precisely, if a and b are both in f of x, which is a subset of the real numbers, and a is less than r is less than x, sorry, is less than b, don't know why I said x here. So if you have a point contained within these two, a and b, then r is contained, sorry about that, is contained within f of x. So this is our intermediate value theorem. So if you have a continuous image of a connected space, then you have this intermediate property going on, where if you take 2 points in your image space, and then if you have something contained between them under an order relation, so that is also going to be by the connectedness, as we'll see, in your image space. Here's our proof, and it'll be short, and you can work out the mechanics more on your own. It took me a while actually to wrap my head around exactly why this worked. Hopefully it won't take you as much time. Suppose R is not in f of x, and this is sort of the similar contrapositive method of approach that we're taking as the previous one. So we want R is not in f of x, and to show that x can be expressed as a disjoint union of open sets in some way. So we have a separation of x, or a decomposition that it's not connected. So if R is not in f of x, what are our two separation sets? So in the real numbers, or the extended real numbers if you want to be precise, we take these two sets defined as a and b, so negative infinity to r, and we let this be from r to infinity, right? Then we have, sorry about that, x to be equal to, let's think about this for a moment, f inverse of a, right, union f inverse of b, and this ensures being a disjoint union of open sets, and we have found a separation of x. Hence, we have the proof of the intermediate value theorem, an essential theorem in calculus. And this is going to wrap up our survey of topology in a review of analysis, and in R to the n, we kind of ventured into that with Euclidean supremum metrics. And we're going to look now at differentiation, which is going to require a bit of a paradigm shift in how we regard the derivative, let's say, in just one dimension. And it'll incorporate some ideas from linear algebra. So it is going to be very interesting, and I hope to see you in the next video after now we've looked at our topology. So thank you for watching.